Honors Chemistry, and welcome to the Through 9.6 Guided Practice. This is our asynchronous discussion. All right, so first let's review the organization of electrons inside an atom, right? And this is obviously with the QM model because that's the one that is the currently accepted model. So first we have our shells, right? And that's our first level of the hierarchy, right? And every shell is composed of subshells, where subshells are so shells provide your approximate distance from the nucleus, right? Where the first shell is closest, the second one is further, the third one is even further, right? Each shell, again, is composed of subshells, right? Where the subshells are places in three-dimensional space where an electron might be found, right? So an S subshell means the electron might be found in a spherical region around the nucleus, right? A P-shaped subshell means that an electron is likely to be found in a lobe region extending on either the X, Y, or Z axes, right? And so forth and so on, right? So a subshell is the place in three-dimensional space where an electron is likely to be found. Beyond subshells, we have our orbitals, right, where the electrons actually are likely to be found, right? And then we have our actual electrons. So shells, subshells, orbitals, electrons. All right, in terms of filling order, right, we have two guiding principles off bow, which says we fill lowest energy up, which means we're always going to start at the lowest energy orbital, subshell, shell, and then we're going to work our way up, right? Hund's rule says that if we have a set of degenerate orbitals, right, where what does that mean again? Right, that means equal in energy. So if we have a set of degenerate orbitals, we will always do what? Right, we will always split and then pair. Meaning we will singly fill each orbital, and then once they are all singly filled, then we'll go back and pair them up, okay? Now, ways to express an electron arrangement, right? We have our orbital diagrams, right? Which are going back to your book, right? And going back to the last lecture, right? We would start with 1s, right? Where the 1 symbolizes the shell, this symbolizes the subshell, right? This symbolizes the orbital, and then we would use some arrows to symbolize our electrons, right? Yes, ring a bell. All right. Now, we also have our electron configurations, right? Where we would simply say 1s2, right? Where now this is my shell, this is my subshell, and this is my number of electrons in that subshell, right? Because orbital diagram would be like the full writing, right? And so kind of like if we write in like block letters, right? Every single letter all the time, right? And when we get to electron configuration notation, right? That might be like writing in cursive, right? Where it's hypothetically a little bit faster, right? And somebody has to sort of be a little bit trained to read it in order to really understand what you're saying, right? Because you're not writing down all the pieces of information necessarily, right? And then we have noble gas notation, which would be like shorthand, okay? Noble gas notation is the shorthand version, and when we do some practice, we'll talk about how to do that, but we will use the noble gas before, just like your book says, use the noble gas before, right, as like an abbreviation, okay? So for example, right, if I wanted to do noble gas notation for magnesium, I would use the noble gas that came before it, right, which would be neon, yes? If I wanted to do noble gas notation for, say, bromine, I would use the noble gas that came before it, which would be argon, yes? So whichever was the noble gas before that element, okay? So then what that means is that argon is the noble gas for all the elements in that period. Yes, does that make sense? All right. Okay, so let's go ahead and do some practice together, right? So it says that we are going to write an orbital diagram, which again, long form, right? An electron configuration, which would be that medium form, for each of these, right? So for beryllium, what's the first thing we need to know? Right. Let's go ahead and figure out how many electrons beryllium has. Beryllium has 4 electrons, right? So I need to put the locations for 4 electrons, right? And if we think back, right, we have our 1s, 2s, 2p, 3s, 3p, 3d, right? 4s, 4p, 4d, 4f, right? And then we would do our diagonal rule as needed, right? Or just memorize them, whichever works for you, right? And I didn't draw the whole table out because we don't need much more than that for this set of elements, right? So anyway, for 4 electrons, we would start with 1s. That's where they always start, okay? They always start lowest energy up, which means that by default, after enough practice, you kind of have a bunch of this memorized. But anyway, 1s, right, we would put our shell, subshell, and our line representing our orbital, and we would fill in 2 electrons. After 1s, we will go to, correct, 2s, and put 2 more electrons, and then we would be done. And then we would say 1s2, 2s2. Yes? All right. Let's go ahead and do the next one, which is a sulfur. So we need to go find sulfur, which is right here with 16 electrons. And what I recommend now is that you pause and then check your answer and see how it goes. So again, we start at 1s, 2s. After 2s, it says we go to 2p. So, this is where you got to remember, p's come in a set of 3 orbitals, right? So 1, 2, 3. And so these would be our 2p, 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 right? And again, we would spread 1 to each. And then we would go back and pair. How many electrons have we housed? Right, 10. After 2p comes 3s. That's 12. And then after 3s comes 3p, which is another set of 3, right? And then so 2, 4, 6, 8, 10, 12, right? 13, 14, 15, 16. We have done sulfur. Then we can do our shorthand, which says 1s2, 2s2, 2p6, 3s2, and 3p4. Yes? All right. And finally, potassium. So let's go find how many electrons potassium has. 19. So if we were going to do potassium, what do we have to do? Right, it's just sulfur with 3 more electrons, right? Which is again why, like I said, it sort of becomes easier once you practice, but you have to do the practice, right? So 1s, 2s, 2p, and then 3s, and then 3p. Now here, we've got to be mindful. How many electrons are we doing? 3 more, right? So if we look here, right, that means this is full, and we will have gone 1 more, right, beyond 3p, which would be 4s. I don't know why I put that up there. So 4s, and 1 more, yes? And then for our shorthand, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Yes? All right, practice, so very important. All right, next up, write electron configurations and noble gas notation for each, right? So again, we need to figure out how many electrons each of these has, and then we can go ahead and answer the question at hand. So fluorine, gallium, and zirconium. Fluorine has 9. You know what, let's just do all these. Gallium has 31, and zirconium has 40. All right, so here, now that we're at this point, what I would recommend is you push pause, see what you can do, and then check these solutions. Okay, so then if we're looking at how to do these, right, so this part should be pretty straightforward because that's just following the filling order that is in the book and is in the lecture from yesterday, right? The noble gas notation. So again, we use the abbreviation of the noble gas before, right? So when we think about what that means, let's get a different color here, right? So for fluorine, right, it's not much of a shorthand because fluorine is right here. Helium is the noble gas before it. Helium has 2 electrons, right? Which means that these first 2 are helium, right? So then here are our first 2 electrons, right? And we would write everything that comes after that, right? Which is sort of like saying these are our core electrons and these are our valence electrons, right? That's kind of what noble gas notation sort of separates for you visually, right? Core versus your valence, right? So same thing for gallium. Gallium, right? If we take a look at where gallium is on the periodic table, we would go to the noble gas before it, which is argon, right? Which is 18 electrons, right? So we would find the first 18. And then those make up gallium. Nope. Those make up argon, and then everything else is our valence, right? Here is our first bunch of electrons that make up our core, and then here is our valence, right? And all of that matches, right? Same thing with a zirconium. We would go find here's zirconium. The one before that is krypton, right? Krypton has 36 electrons. So then all of this is krypton, right? So here we have, again, core versus our valence. Yes? All right. Thank you for listening. Stay tuned, and there is some homework for tomorrow and practice that you should do. All right. Thanks for listening. Be good, and I will see you soon. Bye.